All right, so the limit of a function of two variables. So it's going to be denoted the limit as the pairs xy approach some point AB in the plane of this function f of xy is equal to L. So we're going to see that it's a little bit more difficult to define limits in terms of functions of two variables, and even more difficult for functions of more than two variables. So what we're going to do is we're going to go back to the definition of the limit. So the limit of a function of two variables is equal to a number L. Let me write this. If, so for every positive number epsilon greater than 0, there is, or we can find, a positive number delta greater than 0, such that, well, the absolute value of the function minus L is going to be less than this number epsilon whenever the length of this vector x minus a, y minus b is less than delta. Okay, so notice that what this vector is this is the vector connecting the point xy to the point AB. So what we're really saying is that when the point x comma y is close to the point AB, and what we mean by close is in the length or the distance between those 2 points is small, we have that the actual absolute value of the scalar valued function f and the difference with it, with this number L, is small with respect to epsilon. So it's very similar to the definition of the limit of a function in terms of one variable from the definition. And we can extend this definition to functions of more than two variables as well. So now that we've seen the definition of the limit, let's actually talk about what it's actually saying. So recall that the domain of a function of two variables is going to be some region in the xy plane, like this. So our function f is going to take some region here and map it to, well, some subset of the real line. Now what we're saying is if we take a point in this region, call it AB, then we have a number L over here, and here's L plus epsilon, here's L minus epsilon, so this is a little open interval around L. But now what we're actually going to have in the domain of f is a little ball, a little disk of radius delta. And now what the definition of the limit is saying is that the limit of f approaches L as xy approaches AB if our point xy is in this disk. For this delta that we found, we always know that f of xy over here is within epsilon of L. So geometrically, this is what's happening. If we get close enough inside a small little disk around this point AB within some delta, then our function is going to output within epsilon of this number L. So this is just a pictorial representation of the limit of a function. But wait a second. there's actually a big problem. Because if you recall, for a function of one variable, if we look at a point A and we want to look at the limit, well, we really just need to look at the left-hand limit and the right-hand limit. So from the left and from the right, this function is approaching the same value, so the limit exists. But if we look in the two-variable case, the problem is there's actually a lot of different directions that we can approach a point AB. So for instance, instead of just looking from the left or from the right, I could approach in the domain of the function along this curve right here, or along this line right here. Whereas before I was just approaching from the left or from the right, so I had two things to check. I actually have infinitely many directions that I can approach this point AB. And I actually need to verify that all of the limits from all of these different directions are the same. So that seems really daunting. But however, we have this epsilon delta definition about this delta ball right here that says actually it's okay to think in the vector sense, or a distance from the point AB, as long as I'm close enough, my output is close to my limit value, L. So that's why we're kind of reverting back to the limit definition. But as we'll see, limits are going to work out more or less the same way. There's only a few special cases to look out for. So the last thing we want to talk about with limits is this idea of continuity. So recall, for a function of one variable, f will be continuous at some point x equals a if, well, the limit exists as x approaches a of f of x, and that limit is actually equal to the function value at a. Well, we have exactly the same situation for a function of two variables. We have f of xy is continuous, this time at some point AB, if, well, it's exactly the same thing. We have that the limit as xy approaches AB, now this is going to be from any direction, so this limit needs to exist, but it better equal the function value at the point AB. So the idea of continuity is almost exactly the same for functions of two variables, and even for functions of three or more variables. All right, so this is going to be a marquee example of what we're talking about, with the limits for functions of two variables being more complicated than limits of functions of one variable. And so to show that a function of one variable has no limit, we would just check the limit from the left and from the right. But here we actually have to think about the points xy approaching the origin 0, 0 from really infinitely many ways. And now all we need to do is just find two of those directions where the limit has different values. So let's actually sketch out our domain, which is the xy plane in this case. Now 0, 0 will not be in the domain of this function, but that's okay. We're just looking at the limit as these points xy approach 0, 0. So the function doesn't have to be defined there. So the first direction let's look at what happens if we approach the point 0, 0 along from the positive x-axis. So let's take xy approaching 0, 0. And now notice we have to make a choice about how we want to approach the point 0, 0. So I'm going to approach 0, 0 along, along the positive x-axis. And so how do I actually do that in the limit? Well, what I want to do is if I'm approaching along the x-axis, notice the y values are going to be 0. So my limit as x, y approaches 0, 0, in this case, is going to be the same thing as the single variable limit is x approaches 0 from the right of, well, I'm just going to plug in 0 for y. And this is going to represent approaching the origin 0, 0 along the line y equals 0 from the positive x direction. So what I'll do is just plug in 0 for y, and notice that I just get 0. If I plug in 0 for y, I have 0 over x squared, but x is a small positive number, so then this is really just the limit of 0, which is 0. So if I take the limit of this function as x, y approaches 0, 0 along this segment here, along the positive x-axis, I get a limit of 0. So if the limit exists, if I took another direction, then I should get the same limit. But look at what happens if I take the limit is x, y approaches 0, 0 along the line y equals x. So here's the line y equals x. Now what I'm going to do is I'm going to approach from this direction up here. Now notice I have infinitely many choices for direction. I'm just considering 2. So now I'm going to look at xy approaching 0, 0 along the line y equals x. So if I'm looking at along the line y equals x, I just want to literally set y equal to x in my function. And the limit as xy approaches 0, 0 along this direction is just the same thing as the limit as x approaches 0 of, well, I'm going to set y equal to x, so I'm just going to have x squared on top over 2x squared. But this limit, this is just a standard indeterminate form, so I can use L'Hopital's rule or whatever, and I get 1/2. So this is extremely interesting. So we have two different limits approaching the same point from two different directions. So that means the limit does not exist. Now, if the limit exists, then no matter what direction I approached the point 0, 0, I would have to get exactly the same limit. All right, so we want to actually find the following limit. And now we saw in example 1 that the limit will fail to exist if we approach the point from two different directions and get two different limits. So I need to be very careful in my manipulation here that I don't just approach the point 1, 1 from one direction, that I have to make the direction arbitrary. And so what I'm going to do is I'm going to do something very similar to what we did in Calc 1 when we have kind of this indeterminate form. So notice if I just try to plug in the point 1 comma 1 into this function, I'm going to get 0 divided by 0. So I'm going to have to sort of change the function in some way so that I can actually see what the limit is. And so notice that this limit is the same as the limit of this function. And what I'm going to do is multiply by the conjugate of this bottom right here. Square root of y plus square root of x, and then square root of y plus square root of x. And now there's one problem when x and y are 0, but I'm only considering values of x and y that are really close to the point 1, 1. And so if I actually perform this multiplication, I have in the top y minus x times square root of y plus square root of x over, now this is the whole reason I did this, this is a difference of squares. So I'm going to get y minus x in the denominator. And now look what happens. I can actually cancel the factor of y minus x. And now why can I do this? Because notice that points, so in Calc 1, we can never cancel things that were equal to 0. That would be like dividing by 0. But notice that y equaling x, which is exactly when this term is 0, is not even in the domain of the function, right? So I can't even plug in y equaling x into the domain of the function, so there's absolutely no problem with canceling these factors here. Because when I get near the point 1, 1, even though there's going to be a problem when y equals x, looking along that direction, that's not in the domain of the function, so there's no problem. And so what I have here is the limit is xy approaches the point 1, 1 of just square root of y plus square root of x. But now this is algebraic function, so it's just square root of y and square root of x, and that's going to be a continuous function. So this limit is going to equal the function value at 1, 1. But if I just plug in x equals 1 and y equals 1, I get 1 plus 1, which is equal to 2. All right, so here we have another limit that we're trying to take. And now this function is continuous where it's defined. So if we just try to do the naive thing and plug in 1 for x and 1 for y, we're going to get sine of 0 divided by 0, which sine of 0 is 0, 0 over 0, that's an indeterminate form. And so we're going to have to think a little bit harder. Well, if you recall from Calc 1, we have a very famous limit that we actually know what the limit is. And that's sine theta divided by theta. We know that this is equal to 1. And now this theta can be anything as long as it's approaching 0 and we have exactly theta in the argument of sine and we're dividing by exactly that same theta. And so that's not exactly what I have here. I have sine of x minus y, but I don't just have x minus y on the bottom. I actually have x squared minus y squared. However, x squared minus y squared is a difference of squares. So I can rewrite this limit. So I'm looking as xy approaches the point 1, 1 of sine of x minus y divided by x plus y times x minus y. All I did was just factor the denominator and rewrite the limit. But now look, this is exactly the setup we're looking for. We have sine of x minus y divided by x minus y. That's just the setup we have here. This, in the limit, as xy approaches 1, 1, that's going to cause this to go to 0 and this to go to 0, and because they're exactly the same thing, that's going to be 1. So this is going to approach 1. But then what's left? What's left is 1 divided by x plus y. So I still need to take the limit as xy approaches 1, 1 of 1 over x plus y. But this is not a problem because 1 over x plus y is continuous and that function is defined at x equals 1 and y equals 1. So this is equal to 1 divided by 1 plus 1 or 1/2. All right, so we want to know what values of xy, or pairs xy, is this function continuous? And now, this function is actually the composition of continuous functions. So I'm looking at 1 and I'm dividing by y squared minus x, but y squared minus x is just a polynomial. So that's not going to be a problem. It's going to be continuous because y is a continuous function, x is a continuous function. If I square y, that's a continuous function. And if I take the difference of continuous functions, that's continuous. The fact that it's multivariable really doesn't matter. But now I'm taking the quotient, I'm dividing by something. So this rational function here is going to be continuous wherever the denominator is non-zero. So f will be continuous whenever y squared minus x is not equal to 0. Now, the interesting thing about this question is that this is actually sort of a two-dimensional restriction. It's not like saying, okay, x doesn't equal 5 or x doesn't equal 3. It's saying that y squared minus x can't equal 0. Another way to say this is that y squared can't equal x. Or if we want to think about this as y as a function of x, y cannot be x and y cannot be minus x, just taking the square root of that not equality. And so what does this mean? Well, let's look at the xy plane. So this means that f is going to be continuous everywhere in all of the xy plane, or R2, except for, this should be y not equal to square root of x, and y not equal to minus square root of x, because I took the square root of both sides. So there we go. So we want the entire plane, except we want to remove y equals square root of x. Here's y equals square root of x. Here's y equals minus square root of x. And we're sort of cutting out these two curves from the xy plane, but f is going to be continuous everywhere else, all over here and all over here, but not along this dotted path right here. All right, so again, we just want to find the set of points x, y, z for which this function is continuous. And now the interesting thing here is that our region where this function is going to be continuous is actually in three-dimensional space. So for a function of two variables, it's just going to be in the plane, or two-dimensional space. Okay, so let's see what's happening here. We have a function, natural log of x plus y plus z. X plus y plus z is continuous. Log is continuous. So the composition of continuous functions will also be continuous wherever that function is defined. So where is this function defined? Well, we can't take the log of a non-positive number, or a number that's 0 or less than 0. So what that means is that x plus y plus z better not be 0 or negative. It better be strictly greater than 0. But what does this mean? Well, x plus y plus z equals 0 is a plane that we can actually plot in three-dimensional space. So let's take our time here, since plotting in 3 dimensions is a little bit more difficult. So what we want to plot is the plane x plus y plus z equaling 0. And then we want to take the set of points that's larger or above this plane. Okay, so where is this plane? Well, notice that when x and y are both 0, well, we're going to pass through the origin, right? Because if x is 0, y is 0, and z is 0, x plus y plus z is equal to 0. Okay. So we have a point like that. And then we're also going to point, so I'm going to use the fact here that 3 points will define a unique plane. Okay, so notice that, for instance, when x is equal to 1 and y is equal to 0, z is equal to -1. So there's 1 in the x, here's 1, -1 in z, so we have this point here. And then we can do the same thing with y. If x is 0 and y is 1, z is also -1. So we just go down 1 right there. And so this plane is going to be determined by these 3 points, and we can sort of imagine it's leaning into the z-axis that way. So there's our plane passing through those 3 points. And now we're considering the set of points for which x plus y plus z is greater than 0. So we're looking at points above this plane. So all of this space, I know the picture kind of gets destroyed here, but there's our plane. All points above this plane is what we're considering. That's going to be the points for which this function is defined and hence continuous. And notice that we are not including points in the plane because x plus y plus z has to be strictly greater than 0.